So the third frontier I want to discuss today, which is really exciting and very, very important also clinically, is what we call brain-machine or brain-computer interface. The interface between the brain, which is a machine, but a very special machine, and the machines we build. For doing that, for being able to interact with the brain, certainly the anatomy is not enough. Okay? Anatomy is a static thing. The anatomy may change in terms of structure, and we'll show you later on, when I'll talk about plasticity in the brain, I'll show you that when you learn, there are changes, anatomical changes in your brain, but in order to interact with the brain online, I need to read the signals within the brain. Not only the anatomy, so I need to read the electrical signals in the brain. So on top of the anatomy, on the foundation which is anatomical, there are all these signals. We'll talk about the electrical signals in the brain, what type of signals. All these signals are running, so to speak, on the circuit, and these signals stand for something that the circuit wants to convey. So in particular circuit, when there are particular signals, it means that I need to move my hand to the right and so on. So in order to really read out what is happening in the circuit in terms of information, I need to read the electrical signals. And as I said, we'll focus a lot about the electrical signals in lesson 3 and 4. So how do they look, these electrical signals that are being used to process information, to send commands to my hand or to my mouse or to my thought or to my feeling? So the idea is the following. You go to a particular brain region, let's say here. You know that this particular brain region from previous studies is responsible, let's say, for movement. If you zoom into this brain region, of course, you'll see networks, anatomical networks of neurons. If you zoom out, you see a big network, many cells, billions of cells within this network, and you may record using electrodes, very, very fine electrodes that implant or impale into this region, into this particular one cell. And you may listen, so to speak, to the electrical activity of this one cell. So here is how it looks. So this is the electrical activity of a one cell in the brain of a mammalian, in this case, in the cortex, when the animal is doing something. So you see that the brain fires, we call it fires, some electrical activity. We can put it into a loudspeaker and you can hear, of course there is no sound within the brain. These signals do not make sound, they just change in electrical activity. But if I connected to a loudspeaker, you would hear what you heard, ta 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 ta. This is, so to speak, the barcode of the brain, if you want to call it this way. We call them spikes. There will be a whole lesson about spikes, but you just saw the spikes that a single cell generates. Each cell generates its own spiking activity. So if you would recall from many of them, you will hear a complete music, a complete noisiness of the network, but each cell has its own particular kind of spiking activity. And overall, the message to move my hand up or down is running in these spikes. So all these spikes stand for a particular movement, if this is in the motor cortex, or a particular feeling, if this is in other regions, or a particular picture, if it is in my visual cortex. So, but the common language that we shall talk a lot about, the signals themselves, the common language are these spikes. And so the brain is using spikes to represent the world. So there is no music in my brain. There are no movies in my brain. There is no movement in my brain. My brain generates this electrical activity, and when it generates this electrical activity, I believe that there is a movie there. And when it generates this electrical activity, I'm moving my hand, and so forth. So spikes are very important, and I need to be able to read them somehow in order to interact with a machine that I want to, let's say, activate a robotic arm directly from the brain. So this is a kind of a sketch summary of what I said. So there is a particular region in the brain here, let's say the motor region, the region that activates movement. So let's say this is the region. Typically when this region is active, now it's active, it goes through my spinal cord, so the fibers that goes from this region go through the spinal cord and activate a movement. That's the normal case. But I can also use the same signals, if I can read them correctly, analyze what they mean to say, the signals, the network, and eventually activate a robotic arm. This is extremely useful when there is, let's say, spinal cord injury. Because when there is a spinal cord injury, the signals are being generated in the brain, but nobody listens, so to speak, because there is this cut. Or when I'm an amputee, so the signals are going into my limbs, but I don't have limbs, so I cannot move. So we can today use the signals online, in real time, using many recording electrodes from a particular network, analyze them in real time, and activate a robotic arm. So I want to show you an example of doing exactly that. Recording from the brain of a monkey in this case. The hands of the monkeys are tied. He wants to move his hand because there is something attractive there, and so we can do that. So here is the monkey. Here is a robotic arm separated from the monkey. So the robotic arm is on the side, and there will be food coming here. The monkey can see the food, and he wants to eat. His hands, as I said, are tied, so he generates the signals which we can read. Andrew Schwartz from University of Pittsburgh can read online hundreds of cells together and then activate the robotic arm. Let's see how it goes. So here is the food. The robotic arm is activated directly from the brain of the monkey. The monkey thinks about the movement, generates this electrical activity, and he moves the robotic arm directly from the brain to pick up this little piece of food. That's very impressive. This is brain-machine interface. There is a brain, there is a machine, and the brain activates the machine. In this case, in a most beautiful, smooth way. You can see that he uses the fingers, so he activates the fingers from the robotic fingers, he activates the limbs and so on. Eventually, he gets the food very smoothly. That's amazing. That's amazing. That's brain-machine interface, self-feeding with a robot, and very useful for cases of amputees or spinal cord injury. And actually, there are already people going with this technology with electrode implanted in the brain, and are eating and moving a robotic arm. The opposite direction, the other direction of brain-machine interface, is from the machine to the brain. Before I showed you how the brain activates a machine, now I want to show you how a machine, in this case a battery, which is a machine, activates a particular brain region. And this came basically, or the idea came actually already from a machine activating our heart. So there is a pacemaker to some people who have pacemaking problem with the heart. There are this battery that inject electrical activity, but I'm going to show you that the same technique can work to the brain. And I'll show you now how was it developed. So in this case, there is a recording deep, not in the cortex, but deep inside the deep region of the brain, the basal ganglia. You can record electrically from there. This is Hagai Bergman from the Hebrew University. And when you record from this area with several electrodes, this is one electrode, another electrode, a third electrode, you can see the normal electrical activity in this region of several cells. So one cell is doing ta-ta-ta-ta-ta-ta-ta-ta, stop, ta-ta-ta-ta. Another cell is firing more vigorously, ta-ta-ta-ta-ta, very, very strongly. And the third cell is doing it less, each one with his own electrical music. So this is a normal brain in this region. In Parkinson, apparently, when you are sick with Parkinson, this same region, the cells in the region, are generating different electrical activity. We can say a wrong electrical code, because suddenly the cells are starting to fire these spikes, but in a very different pattern. You can see ta-ta-ta-ta-ta stop, ta-ta-ta-ta-ta stop, like a machine gun, ta-ta-ta stop. Not only that, but the cells seems to fire similarly. Unlike here, that they were different, here they seem to synchronize together. And so the whole network is doing like this: fire, stop, fire, stop, ta-ta-ta-ta-ta, stop, all of them. And this wrong code, this oscillatory activity in the brain, the manifestation of it, the output of it, part of the manifestation is this tremor of Parkinsonian patients. So the idea was, and is very, very effective today in many, many hospitals, is to take this pacemaker, this battery that is implanted here below the skin, to generate signals in the battery, tack, 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 with a particular frequency and strength, which you can manipulate, and inject this current into this region that I just showed you, where you have a wrong code, wrong electrical activity if you are a Parkinsonian patient. And so you want to intervene, you want to somehow affect, and we don't completely understand to the end why does it work so well, I'll show you in a second, why does these signals that you from the outside, this machine from the outside inject into this region, suddenly, so to speak, symptomatically, almost completely repair the Parkinsonian symptoms in some patients. So here is a patient, Parkinsonian patient, actually very young person, already about after 10 years of Parkinson. You can see that he has all these very, very, very difficult and very, very sad symptoms, that it's very difficult for him to generate movement. He cannot coordinate movements like this. He's a very, very sick patient. Of course, he cannot drive like this. It's very hard for him to go to the grocery. So this is a very sick patient. And so the question is, after 10 years of medication, what to do? And as I said, one new technology that we call the deep brain stimulation is to stimulate the brain deeply into this region and try to repair symptomatically these symptoms. You can see how difficult it is for the patient to do something like that we do so simply, because Parkinsonian people cannot do that. So let's see what happens to him after the operation. So let's stop this for a second and let's see this same person now receiving this pacemaking from this battery. So it is activated now, and you can see how well this person looks. It's the same person. Some months after the operation, you can see that he's doing things that are very untypical to Parkinsonian patients. So this is the intervention, this is the interaction between the machine and the brain. That the machine fixed, so to speak, at least symptomatically, the Parkinson, and the person really can walk and really can drive, and I mean the quality of life is now really improved dramatically. Of course, when you turn off the machine, the Parkinson symptoms will come back immediately. So it's a symptomatic repair. So this is beautiful, and this is really a direction that we go, because we want to repair brains and we want to impale to the brain. And I just want to show you, just to complete this part, the future challenges of brain-machine interface. So one challenge is to interact with the brain in a telemetric way. First of all, you want to put some kind of a chronic recorder or chronic probe that will listen, that will record the electrical activity of many, many cells. So you don't want to put wires and electrodes. You want to use nanotechnology in order to put chronically a little piece of machine into the brain that will telemetrically send the signal outside of the skull. So this telemetric communication with the brain, both from the brain outside, but also maybe to stimulate the brain telemetrically if we can do it to a particular region. This is the future. It does not exist yet. Some of it exists, but not all. The next challenge is to really analyze. You saw before, you need to do it in a real time. The analysis of the signal has to do in the real time. So the monkey or the person thinks about movement, you need to now move the hand. You cannot wait an hour. So it's a real-time signal analysis, real time. And if you have millions of signals, as Obama's project is to have million or billion of signals simultaneously, this means that you have to be able to analyze all these signals in real time, and which is it's a challenge for signal processing community. So this is another challenge, to develop these methods. Then, of course, the challenge is to develop a robotic arm that is very sophisticated. So our arm is very sophisticated with many degrees of freedom, and I can do that and that. We don't yet have robots as sophisticated in terms of arm movement, but there are developments towards this direction. And finally, and that's very, very important, when I'm moving my hand and I'm touching something, so I'm touching this bottle now, I get also feedback from the fact that I touch. So I not only move, but I also get information about that it's a plastic, that it's soft, that it's cold. All this information comes from sensors in my hand, in my fingers. Sensors that are going to another region in the brain, the sensing region, somatosensing. So we need to put in this robot sensors when the robot will, so to speak, touch a bottle or a glass or somebody else, there should be an information closing the loop. So movement and closing the loop in terms of touching. That's another challenge. So this is the future challenges from brain-machine interface.